Welcome back, friends. So we have been looking at positive and negative energy solutions of the Dirac equation. This is after studying uh, the covariance of the Dirac equation. So what we have seen is that in the momentum space we can simply write down the Dirac equation in this particular fashion, and then we can derive the solutions in this the U and positive energy solutions and the negative energy solutions in this fashion essentially. So you have written the positive energy spinor U in terms of this particular thing. So U of P bar P and S P bar essentially is this the vector P momentum space vector is given in terms of root of E plus m 1 sigma dot P bar by E plus m. Okay. And some the spin part essentially, which is either plus half or minus half. Given this, so similarly you can write down the negative energy solutions in this particular fashion. I remember that the spin part is essentially a 2 component spinor, and it is multiplied the 2 component part on the upper 2 by 2 part of this column, and this one is essentially again it's a 1 it's a column which is written as a 1 which multiplies this I sigma to chi of s essentially. Okay, very good. So we will continue to looking at some solutions of the properties of the solutions, some properties of the solutions of the Dirac equation. This is all in momentum space. So because this makes life easier for us. So what we have is so we can re-express the solutions in this fashion: P slash minus m u of 0. This is a positive energy solution of the Dirac equation. P slash plus m times v is equal to 0. So this is the negative energy solution of the Dirac equation. This is the positive energy solution. Negative energy solution. So remember, P slash is a matrix and m is a column vector. This we have seen it, and remember this entire fashion we have seen in great detail here. Okay, this sigma dot del bar we have made it into P slash. Okay, we have seen the form of this P slash in the beginning also essentially. So this is nothing but your P slash and everything. So just to confirm that this is what we have written. These are 4 component spinors U and V, and this 4 by 4 matrix annihilates or makes this acting on U should go to 0. That is how you define your solutions, okay, in this particular fashion. Now there are some properties like if you change the sign of the momentum, if one changes the sign of the momentum of the say for example, so V1 you have which I will essentially leave for homework. So V1 of P mu is equal to U3 of minus P mu. You have these relations essentially between the positive and negative energy solutions, because you can always change the sign of the momenta, and and you get back the second part of the positive energy solution, essentially the second part. So, if you where what I mean is that, so you have 4 components of the U spinor. So, U spinor has U1, U2, U3, U4, and V spinor has V1, V2, V3, V4. Okay. So, what I am saying, this can be seen, U and V we have written explicitly in this particular fashion. This fashion. So, here you see U, okay. Similarly, we have written V. Okay. So, you see the upper part of V can be equivalent to the lower part of U, okay, lower 2 components part of U by a change of sign of momenta, essentially by a change of sign of momenta. Now, these are certain things which you can know essentially, okay, and this I leave it for homework essentially. You can study these things at homework. Good. Okay, let us proceed further. There are some important relations between relations of the spinors. So, these solutions are complete and orthonormal. These are complete and orthonormal to each other. So, you have U bar P of S So, the inner product of 2 U vectors is always normalized to 1, essentially the 2 spinors. Similarly, the inner product of 2 V vector is also normalized to 1. So, these are they are orthonormal, okay, and they are also, this we have seen it last week also, essentially in the last class, Ps V of Ps is equal to 0. So, they are orthogonal to each other, the U spinors and the V spinors are also orthogonal to each other. Now, this helps us to actually make we built wave functions, right, essentially. So, these wave functions can be now you can worry about that you can actually make sense out of these wave functions such that they keep the probability conserved essentially. There is also one more set of while this is like an inner product of the spinors, there is also one more relation between these 2 spinors which makes it very important when we are calculating amplitudes, when we are looking at process including including say electromagnetic theory or one of these things, essentially interactions. So, the other important relation is completeness relation, which is like an outer product. So, U of S P U bar of S P is equal to P slash plus M. Now, you see this is U bar. So, the previous one is U bar U. So, this is like outer product essentially. So, this is UU bar. Similarly, you have some more S is equal to 1 to 2 V of S of P, V bar of S of P is equal to P slash minus M. So, this is like outer product in of two vectors. Okay. This is like vector, but this today here these are spinors. This is the outer product of the two spinors essentially. Okay. Well and very good. So, you have we have seen the solutions of the Dirac equation. We have seen that the Dirac equation is covariant under Lorentz transformations. So, what we need to see is what kind of probability currents this theory allows for you, essentially what kind of probability currents this theory allows you. Now, remember that Dirac theory does not it does not rule out negative energy states. In fact, it meaning Dirac theory, it started off by saying that negative energy states are not meaning should not be there, but the norm of the probability density should always be positive. But in spite of that, you still have negative energy states because the Dirac equation is a representation of the Lorentz group, essentially it is a Dirac. So, in short, if you combine quantum mechanics and relativity, it is relativistic quantum mechanics, or it is inevitable that relativity forces antiparticles on us. Okay. This is some sort of a prediction, okay, that the moment you have relativity, you need to have the moment you use relativistic dispersion relations, one need it automatically predicts the presence of antiparticles. But this before going into further interpretation of Dirac theory and Dirac hole and everything, essentially we will see some more aspects about hole theory and everything. We will see some more aspects about the Dirac equation itself, essentially. Okay. Now, now that we have introduced the particles and antiparticles, let me just say you that let us think of some simple process in which an electron comes in and goes out. This is to introduce a simple process. So, an electron comes in. So, let me just say time is in this direction, an electron comes in and it goes out. While it goes out, it emits a photon, and this photon is seen by another electron at another point, another space time point, essentially. Okay. This is not time. Okay. Time is in this direction. Okay. And so this is an electron E minus, it goes out in this direction, this is an E minus, this is an E minus. So, there is an electron which comes in and interacts with a photon, and this electron goes out. Now, similarly, and this photon is it propagates a distance up to a certain distance where it sees another electron at a distance, and then this electron is repelled by that photon, essentially, and this is what is the process, essentially. So, now what we did here is what we do or in ordinary quantum in ordinary electrodynamics itself. In electrodynamics, what we do if you want to measure the force of a particle, so what we put a small test charge at some point, essentially at some space time point in the vicinity of the original particle essentially. Okay. We put a test charge and then so we want to measure the potential due to the original particle on the test charge. In a similar sense, what we are doing is that because if there is an electron somewhere there, you want to detect its presence or the force at some distance. Okay. Because we are in a relativistic theory, this has to be, there is no longer action at a distance, you need a particle which travels from that particular point to this particular point. So you need, so if you put this as your test particle, test electron, this is the original electron. So the test electron comes here at a distance and the original electron radiates a photon from here and that is how the test electron will see the force due to the original electron essentially. This entire process is done in relativistic field theory in this particular fashion, and this particular thing is called scattering. Okay. Now the reason, so this is expressed in something called a Feynman diagram. What we have written right now is nothing but a Feynman diagram in relativistic fundamental. So what this is a typical process which happens in relativistic quantum mechanics or relativistic quantum field theories. So what these orthonormal relations ensure is that when I compute the probability of such a process, say simple scattering process, the scattering process amplitudes are correct essentially. So the orthonormal and completeness relations ensure you that these processes are in general have probability which is conserved, essentially they make sense, essentially the probabilities are sensible. So you do not have unphysical results essentially. So this entire processes in the scattering process in relativistic quantum mechanics or relativistic quantum field theories are encoded in something called an S matrix. What is called as an S matrix, which is nothing but a scattering matrix. Remember in relativistic field theories we do not really have relativistic quantum mechanics, you do not really have action at a distance essentially. Now before coming to that we need to okay. So now before coming to understanding this thing, the one of the basic ingredients, so this is the motivation if you want to understand S matrix in relativistic theories essentially. So for this motivation we need to see what are the probability currents associated with a Dirac equation, Dirac solutions essentially, the Dirac wave function. What are the currents, meaning because we remember when we did the Klein-Gordon equation we saw that the current the interactions which we included in the Klein-Gordon equation in relativistic field theories are included in terms of a current in the probability current which is psi bar del mu psi. Okay. Let me recap essentially, let me recap Klein-Gordon equation. With EM field in the presence of electromagnetic field, what we wrote down for the Klein-Gordon field was we introduced the minimal coupling, okay, del mu okay, goes to del mu plus I E A mu, where A mu is the vector potential of the electromagnetic field okay. We introduce the minimal coupling okay, and that is how we introduce the current coupling, the main current, the probability current or the charge current of the Klein Gordon particle wave function phi, if you remember, is J mu is equal to phi star del mu phi minus phi del mu phi star. So this is a Lorentz current J mu, okay, I should put the index correctly, it's a Lorentz vector. So there is a Lorentz vector. So the question is what kind of currents, okay, what kind of currents does the Dirac wave function allow you. So what kind of currents that the Dirac wave function allow you, which transform differently under the Lorentz symmetry, essentially which transform differently under this Lorentz symmetry. So the J mu, the current which we introduced for the vector potential or which couples to the vector potential in the Klein Gordon wave equation essentially is a vector current, Lorentz vector current. So what I mean, so you should remember when I say vector, here it means vector, it transforms like a vector under Lorentz symmetry, okay. So the question is similarly, okay, similarly what are the currents associated with the Dirac wave function. Now remember, Dirac wave function is different because Dirac wave function is a spinor. Here phi itself is a scalar, phi itself in the Klein Gordon field, the phi itself is a scalar, and that is the reason why you need to put a del mu to make it into a vector current. Essentially you need to put in a vector current. So what is the one which makes it a vector is a del mu. Remember, del mu transforms as a vector under Lorentz symmetry. Okay, what makes it into a vector is the del mu essentially, what makes it into a vector, and okay. So the same questions which we are going to ask essentially with the Dirac wave function. Under Dirac wave functions you have several kinds of currents associated, which is surprising and also which is correct, because the main reason is the wave function of the Dirac wave function is a spinor, essentially it is a spinor wave function. So the first current associated with the Dirac wave function is a scalar current. Okay. So psi bar psi, psi is a spinor, psi bar psi is a scalar, psi bar psi is a scalar, psi bar is equal to psi dagger gamma 0 psi, okay, psi bar is equal to that. You remember that we introduced this gamma 0, okay, and psi dagger psi bar is equal to psi dagger gamma, dagger is nothing but the Hermitian conjugate, and gamma 0. So, psi bar psi is always a scalar. This I think we discussed also when we just introduced the Dirac equation. So, this is a scalar current. This is a scalar current. The second kind of current which you can have, okay. So, this transforms as a scalar, this transforms as a scalar. How do you know that? Because this transforms as a scalar. You remember that this I think we discussed essentially okay. One way is actually explicitly looking at how psi transforms, okay, how psi transforms under Lorentz transformations and how psi bar transforms under Lorentz transformations, and then check how psi bar and psi transforms under Lorentz transformations, and you see that the Lorentz transformations cancel and everything essentially. Another way you can check essentially is that, because remember that S is nothing but the transformation matrix S which we introduced some time ago is this, is sigma exponential I gamma mu nu I sigma omega mu nu sigma mu nu essentially. So, this you can show that with this you can actually explicitly show that psi bar psi becomes a Lorentz transformations because under S it transforms as and under S bar psi bar transforms as S inverse. So, S bar S transforms in this particular fashion. I think there is a simpler way of looking at it. Actually I think I introduced it some time ago, long time ago when I introduced psi itself. So, that psi 1, psi 2, psi 3, psi 4, if you write it down, psi 1 plus psi 2 square, psi 1 plus psi 1 square, I think I mentioned it that it is not Lorentz invariant long time back. Oh, I am trying to find the notes. Here it is. So, this is it. So, you see that this is Lorentz invariant quantity. This is something which we mentioned long time back. Okay, this is positive definite and Lorentz invariant quantity psi bar psi is given by this particular thing. Gamma 0 has a plus 1 minus 1 minus 1 psi 1 psi 2 psi 3, and psi bar psi has this particular fashion, and this is a Lorentz invariant quantity, and you can explicitly show that it is a Lorentz invariant quantity by explicitly write it down, psi prime bar psi prime is equal to psi bar psi. This is easy to see it, and it psi dagger psi is not Lorentz invariant. Okay, psi dagger psi is not Lorentz invariant. Okay, so that is one of the scalar quantities which is a scalar current. Now, if you multiply this, so this is a scalar current, this forms like a transforms under Lorentz transformation. Now, if you multiply this with some scalar particle, essentially scalar density, essentially probability density scalar particle essentially, and this will give me some sort of an interaction which is called a Yukawa interaction. We will come back to that a bit later, which is useful. Okay. Second one which we will see is a vector interaction, vector current. So, the vector current is psi bar gamma mu psi. So, here we do not have to introduce del mu because gamma mu is already a vector under Lorentz transformations. So, you can have So, you do not need to introduce a del mu, essentially you do not need to introduce a derivative, and the moment you introduce derivative you are introducing momentum into the picture. So, here you do not need to introduce momentum into the picture. So, there is a gamma mu is already a vector. So, this entire thing transforms as a vector under Lorentz transformations. So, I would advise all of you to go home and show that this actually transforms as a vector. Now, you show me that this J mu, call it as a J mu transforms as a vector essentially, okay, under Lorentz transformations. Okay. So, similarly you under Lorentz transformation psi transforms as something, psi bar transforms as another, gamma mu transforms as a vector. This we have seen already. So, you can, if you are clever enough, you can use the transformation of the gamma matrices and show essentially this entire thing transforms as a vector under Lorentz transformations. So, you can the way to show it is you just take infinitesimal Lorentz transformations. Okay. So, you do not have to do the full exponential part, essentially take the first term, expand it, and then you show that this is the term. Before moving further, I will introduce one more thing called the tensor current. The tensor current is also something which this transforms as a tensor under Lorentz transformations. Now, what are the things which transform as a tensor? Any 2 index object transforms as a tensor. Now, what is sigma mu nu? Sigma mu nu is the commutator of gamma mu gamma nu, as I think we had defined it several times. Okay. This is a tensorial current. So, this is some tensorial current which we call it as theta mu nu. We can call it as theta. Okay, we can put it indices on the top. Let me call it as theta mu. There are several tensorial currents, like something like the energy momentum tensor and so on. So, we can, this is this transforms similar to the energy momentum tensor, okay, because it has 2 indices under Lorentz transformations. But this is a completely different current, which is, we will see this also has implications, and Dirac theory has a prediction for this particular current essentially. The Dirac theory has a prediction in the simplest electromagnetic theories of Dirac theory. Okay. So, we introduced 3 currents. One essentially is the scalar current, through which we say that we will couple scalars. If I put a scalar, it will be a Lorentz invariant. I can write an action which is completely Lorentz invariant, psi bar psi phi. So, that will be a Lorentz invariant quantity, that those lead to something called Yukawa theories. And then you have psi bar gamma mu psi. This is nothing but, if you can always couple it with a mu, then it becomes Lorentz invariant again, current transformation. This is nothing but your quantum electrodynamics. Essentially you have electrodynamic theory with an electron and a photon, essentially electromagnetic theory. And the third theory is psi bar sigma mu, third current is psi bar sigma mu nu psi. This is a current which does not appear normally, but it appears at a higher derivative terms with respect to, with the derivative couplings essentially with of the electromagnetic field. It couples to F mu tensor, it does not couple to A mu directly, because it needs 2 rank tensor to make it Lorentz invariant, because the Lagrangian is always a Lorentz scalar. So, it always couples to F mu, but this current is we will see the dimensions and everything, as we will see later on. This current is essentially generated at higher order in perturbation theory. This current does not exist at the lowest order in perturbation theory essentially. So, we have seen 3 particular currents, essentially the scalar current, vector current and tensor current, and from the next class we will see the discrete properties of the Dirac equation, the parity, charge conjugation and so on. So, then we will introduce 2 more currents and then we will start looking at interacting theories with Dirac equation essentially. Okay. So, thank you very much and I will see you in the next class. Thank you.